next topic is a digital filter. So design a digital IR filter from analog IR filter. So last section we have seen the how to design the analog IR filter by Butterworth and Chabashi filter. So there we are finding out in terms of HAFS, correct? So we are getting the transfer function in S domain. So if you want to convert this analog filter to a digital filter, we have to go for the S to the Z transformation. We have to go. So that is from S transformation to the Z transformation we have to go. That means it is converting from analog filter to a digital filter. So there are different techniques we are using here to convert the analog to a digital filter. So one is the impulse invariance method, another one is a bilinear transformation. So first method we'll see here. First method is a digital IR filter designed by impulse invariance method. So in this step 1, what we are doing is we are finding the system function in HAFS. So HAFS equal to this we are writing in terms of partial fraction expansion method. So that is summation k equal to 1 to n ck divided by s minus pk. So here pk is nothing but your poles in the system and ck is nothing but coefficient of partial fraction expansion. So now you know how the system will be. For example, if you are taking this is the system HAFS equal to 1 divided by s plus 1 s plus 2. So if you want to go for the partial fraction expansion method, here we can go a divided by s plus 1 plus b divided by s plus 2. So here a and b are nothing but it is a coefficient of partial fraction expansion. And here the poles in the system, there are 2 poles here, that is the pk. So that is only here we are written, that is ck divided by s minus pk. So in terms of partial fraction, here we are written here. If you are taking the inverse Laplace transform for this HAFS, so here the ck will be a constant. So it will come as it is. The 1 divided by s minus pk, we can write it as a e to the power of pk into t. So next step is we are finding the impulse response of digital filter is obtained by uniform sampling of HA of t. So the digital signal can be obtained from the analog signal. So if you want to obtain, we have to go for the sampling process. So here we have done the same thing only. So first we are finding out the analog signal. So that analog signal, from this analog signal, if you want to get a digital signal, we have to go for the sampling. So we are here, we are sampling at some regular interval of time, that is t equal to, here it is n into t. So if you are substituting here, we are getting it is HA of t. So the t will be replaced by it is n into t. So your equation also it is k equal to summation k equal to 1 to n ck into e to the power of pk. The t value will be replaced by it is a n into t. So now next step is the system function of IIR filter can be obtained by taking the Z transform of H of n. So if you are taking the Z transform of this function, we will get what is your H of Z. So just we are converting the H of S to a H of Z here. So we know the H of Z, the Z transformation formula, that is summation n equal to 0 to infinity H of n into Z to the power of minus n. So this will come summation n equal to 0 to infinity. This H of n will be replaced by this term here. So if you are replacing, we'll get this term that is multiplied with it is Z to the power of minus n. So just here what we are doing is we are rearranging the summation here because we are having the k terms here. So we are rearranging the term summation k equal to 1 to n ck, and here both the term we are having n. So we are writing the summation I am bringing to here, that is summation n equal to 0 to infinity e to the power of pk n into t into Z to the power of minus n, correct? So in this term, both the term n is there, so I can write it as e to the power of pk into t Z to the power of minus 1 the whole power of n. So this we can write it as an infinite geometric sum series formula, summation n equal to 0 to infinity a to the power of n we can write as a 1 divided by 1 minus a. So similarly this equation will come as it is. So this we can write as a 1 divided by 1 minus e to the power of pk t into Z to the power of minus 1. So this is your H of Z. So what we taken is, we have taken your H of S is this is your system function. So we are converting into a H of Z. So if you want to convert, so if you are having the coefficient will come remain same. So only the poles we can write it as a 1 divided by 1 minus it is e to the power of, it is the poles will be multiplied with e to the power of pk into t into Z to the power of minus 1. So here t is nothing but your sampling time period. So for example, if you are taking your H of S as c1 divided by s minus p1, then your H of Z we can write it as a directly we can write c1 will come constant as it is, and this poles we can write as a 1 minus it is e to the power of, instead of pk here we are having p1, so it is P1 into T into Z to the power of minus 1. So this is the transformation from H of S into it is a H of Z in impulse invariant method. So next we'll see how to do the mapping from S plane to the Z plane. So this is the equation which will give the relationship between the S and the Z domain. So here it is Z equal to e to the power of S into T. So here the Z is nothing but it is in polar form. It is real value, that is R into e to the power of j omega. It is real at an angle theta. So here it is R into e to the power of j omega, and S is nothing but it is sigma plus j omega. So if you are substituting here R into e to the power j omega equal to E into S value will be replaced by sigma plus j omega into T. So we are getting the term E into sigma into T, and e to the power of it is j into omega T. So if you are equating the real and the imaginary part, so in the real value we are getting it is e to the power of sigma into T, and the imaginary part we got it as a omega equal to it is omega into T. So this omega is nothing but digital frequency, and this omega is nothing but your analog frequency. So we are getting this term. So in this we can see the three cases: when sigma is less than 0, when sigma greater than 0, when sigma is equal to 0. So that is sigma, it is on the S plane, and how we can map it onto the Z plane. If we are taking the condition sigma less than 0, in the Z plane we can take the condition that is 0 less than or less than 1. Correct? So that means if sigma less than 0 means if all the poles will lie on the left hand side in the S plane. If all the poles lying on the left hand side of the S plane, so in the Z plane means how we'll take in the Z plane, we are taking a unit circle. In that, if R is less than 1, that means if all the poles are lying inside the unit circle, both are same. That is, left hand side of the S plane is mapped inside the unit circle in the Z plane. So that is the meaning. When sigma is greater than 0, if you are taking in Z plane, we can take R is greater than 1. That is, sigma is greater than 0 means all the poles lying on the right hand side in the S plane. But if you are considering in the Z plane, if R is greater than 1 means all the poles should be lying outside the unit circle. So that is RHS of, that is right hand side of the S plane, that is mapped outside the unit circle in the Z plane. So that is the second condition. So here if it is lying inside the unit circle means meaning is the system will be a stable system, and if here if all the poles are lying outside the unit circle, meaning is it is an unstable system. Next one is if sigma equal to 0 in Z plane, that is R equal to 1. Sigma equal to 0 means it is on the j omega axis in S plane, and that is mapped onto the on the unit circle in the Z plane. So that is the meaning. So that is three condition we have seen. This is in the S plane, this is in the Z domain. So here if sigma is less than 0, that means all the poles lying left hand side, that is mapped onto the inside the unit circle in the Z plane, that is R is less than 1. The system will be a stable. When sigma is greater than 0 means all the poles are lying outside the sigma is greater than 0 means it is lying on the right hand side of the S plane. So that means here all the poles are lying outside the unit circle. That means the system will be a unstable system, and it is on the j omega axis means here it is mapped onto the on the unit circle. That is the three conditions we can see here. So next one is digital IR filter designed by bilinear transformation. Here just we have to do the transformation once. If you are getting your HA of S, the HA of S will be, the S value will be replaced by this term here, that is 2 by T into it is 1 minus Z to the power of minus 1 divided by 1 plus Z to the power of minus 1. So using this transformation, so we can convert this HA of S into H of Z. So this is the transformation what we are using in bilinear transformation. So this is the formula we are using here. So this is the relationship between discrete time frequency omega and analog frequency omega. So sometimes they will give the digital frequency value and analog frequency value we can find out by using this formula. So this formula we have to remember. So this analog frequency omega equal to, that is 2 by T into tan of omega by 2, or we can use this formula also. Any one of the formula we can use and we can find out the frequency. That is, this will give the relationship between this analog frequency to the discrete frequency. And next one is we'll do the problems on impulse invariance method. In this they given the transfer function as 1 divided by s plus 1 s plus 2. Find the corresponding h of z using impulse invariant method for the sampling frequency of 5 samples per second. So here we have to go for the partial fraction expansion method. So here we are having the two poles. We'll get a divided by s plus 1 plus b divided by s plus 2. So if you are solving this one, we'll get what is the a value, what is b, correct? So if you are substituting here a coefficient 1, we are getting a value as a 1 and b value as a minus 1. So in that they have given the sampling frequency, they given it as a 5 radian per second, and again this we have to from the frequency we have to find out what is the time t we have to find out. So t value can be found out by 1 by fs, that's what is 0.2. So now already we know that if you want to go for the impulse invariant method, so here formula what we are using is already we know. If it is in this form, that is c1 divided by s minus pk, so your transformation will be the constant will remain same, and then the poles we can write it as a 1 minus e to the power of, here what poles we are getting, that will come p1 into t into z to the power of minus 1. So similarly here this h of z, h of s into h of z, if you want to convert this, we can write that constant will remain come same, divided by 1 minus, here it is e to the power of, so what is the pole here, pole we are getting it is a plus 1, so that become minus 1 into, so here it is t value we got it as a 0.2 into z to the power of minus 1. So this is your impulse invariance transformation. So similarly in the second one, we can, the constant will come minus 1 divided by 1 minus e to the power of, the poles we are getting it is a minus 2 into t value is 0.2 into z to the power of minus 1. So now if you are simplifying, that is e to the power of minus 2 will get 0.819, e to the power of minus 4 0.67, and this we can bring to z inverse, we can bring to the down, it is divided by z. So if you cross multiply, we get z divided by z minus 0.819, and this also we can write z divided by z minus 0.67, and again if you are simplifying, if you are cross multiplying this one, and if you are simplifying, you will get this transfer function. So this is your h of s. So we are converting from h of s into a, it is a h of z by impulse invariance method.